Hello everyone, and thanks for watching Edupedia World videos. This is the fifth and final video in the topic of current electricity, and in this video we'll look at some examples of what happens when capacitors and resistors are connected together, and then we'll see a couple of standard problems and I'll show you how to solve them quickly. So first we'll see the process which is called charging of a capacitor. The name suggests it is the process by which charge is given to capacitor, that is positive charge to the positive plate, negative charge to the negative plate. And when we learned capacitors, we just attached a capacitor to a battery and assumed that the capacitor would end up having the requisite charge. So we might a battery of EMF E to a capacitor of capacitance C, and it would immediately get a charge of plus CE on the left side and minus CE on the right side. But as I said in the previous video, there is no such thing as an ideal conductor with zero resistance. Even a small standard wire has a small resistance. So generally, whenever we are charging a capacitor, we will have a wire which is in series with the capacitor. So if all else fails, we just start writing down the equation, and the equation in this case, if we start from here, let's say this is the zero potential, then the first equation, the first rise in potential will be E, and this is the positive and negative plate. So once we reach here, there will be a drop of potential, so minus, and the potential here would be, if the charge at any point is Q, plus Q and minus Q, then the charge on the capacitor is Q, and the potential difference will be Q by C. So, and that's a drop in potential difference, and as you go here there will be another drop in potential difference because current is flowing in this direction, minus IR. This is equal to 0. From this what I get is CE minus Q minus IRC is equal to 0, or I is equal to CE minus Q by RC. Right, now I will write as dq by dt, and this is the differential equation which we need to solve. CE minus Q will take it to the right hand side, so what we'll get is dq by CE minus Q is equal to dt by RC. We'll integrate this. Initially time was 0, finally time was t. Initially the charge was 0, finally let's say the charge is Q. So the equation we'll get is, now here's a minus sign, so we'll get a minus, right? So first of all we'll get the minus, then the integral of 1 by Q will be log of Q, so we'll get ln Q, right? But we'll first put capital Q and then 0, so ln CE minus Q by, then we put 0, CE is equal to RC, right? So we'll take the minus to this side, and we'll take the exponential power to all of them. So what we'll get is CE minus Q by CE is equal to e to the power minus t by RC, or what you'll get is Q is equal to CE times 1 minus e to the power minus t by RC. Right. Now this is a very important relation because it tells us how the charge changes with time. So initially the time was 0 and the charge was 0. What happens as the time becomes very large? This term becomes very small and Q is equal to CE, which is the value it would have been if there was no resistance. So what happens actually when you're charging a capacitor? This is time and this is the charge on the capacitor. It is supposed to be CE, but it actually never really is CE. It keeps getting closer and closer to CE as time increases. So the general graph is something like this. It will never really approach CE, and that makes sense because let's say it is very near CE, right? In that case, the potential difference across this would be is very near to CE. If Q here is very near to CE, then the potential difference across this capacitor will be very near to E. If the potential difference across the capacitor is very near to E, then the potential difference across this resistor will be very small. If the potential difference across the resistor is very small, then the charge current flowing through the resistor will be very small, and the rate at which the charge increases will be very small, right? So we see this asymptotic sort of behavior where it approaches CE but never really reaches CE, right? The quantity RC is called the time constant of the circuit. and it's a measure of how quickly something charges. If RC is very small, then it will happen very quickly, and if RC is large, then it will happen slowly. Right. So this is the process of charging of a capacitor. The second process naturally would be discharging. And for discharging, we don't really need a battery. We'll just attach an already charged capacitor. Initially, let's say it has a charge Q, plus and minus, and we'll just attach it to a resistor. And what will happen is, if this is plus and this is minus, then this is at a lower potential, this is at a higher potential, let's say V. Right now I'm not using E because E is reserved for batteries. Then there will be a potential difference across this wire, there will be a current flowing through this wire. As the current flows, the charge will decrease because current is flowing from positive to negative, and eventually the capacitor will be discharged. So let's start from here. The equation will be, we go up, so plus V and then minus IR. What is V? V can be written as Q by C, right? So minus I. I'll just use small q because capital Q will use for the initial value. This is equal to 0, or we get I is equal to Q by RC. I is dQ by dt. So we get dQ by Q is equal to dt by RC. Integrate 0 to t. Initially charge was capital Q, finally let's say charge is small q. So this will be ln. So we'll get ln of small q by capital Q is equal to T by RC. Hang on, I seem to have made a mistake because this side is less than 0 and this side is greater than 0. So let's look back. I seem to have... Oh, okay, yes. This is a mistake I've made a few times now in other places. This I... And this is an important thing, so I'm sort of glad I made this mistake to be able to point this out to you. This I is really not equal to dQ by dt. This I is actually equal to minus dQ by dt, because if dQ by dt is positive, that means Q is increasing, then I is towards the left. If the current is towards the right, I, that means this positive charge is decreasing and the magnitude of this negative charge is decreasing as well. Right. So in this specific case, if Q decreases, that means there's a current flowing towards the right. So I will be minus dQ by dt. I'll repeat this again because this is important. If there's a certain amount of current flowing to the right, then what will happen to this Q? Should it decrease or increase? It should decrease, right? Because if there's current flowing, then positive charge is going from this side to this side. It's being neutralized. So Q should decrease. So if I is positive when Q decreases, then we'll have to put a minus sign, minus dQ by dt. Right? So that's where another minus comes from. Here will be a minus. How did I know that I made a mistake? Because Q is smaller than capital Q. So ln of this will be negative, but this was positive. So I knew I made a mistake somewhere. So this is the correct equation. From this I'll get, after manipulating, Q is equal to Q times e to the power minus T by RC. So again we see the same sort of behavior. It initially starts at a value Q versus time, and it decreases, but it never really becomes 0. And it's understandable, because when Q is very near 0, then the potential across these 2 points will be very small. The potential across these 2 points will be very small, which means the current will be very small. So if we are here and the current is very, very small, then the next instant we'll change the charge by a very small amount. Right? So this is the process of discharging of a capacitor. The theory part of current electricity is now completed, but I'd like to take a couple of problems to show you how problems can be solved. So the first, I'd like to take a problem which I'm sure exists in at least every book and many assignments as well throughout educational material that is available. And so I'll do that problem because it's sort of a different problem from the others, but yet is quite common. So it's a problem in which you have to calculate the equivalent resistance. First, let's just do this simple question where all the resistances have a value R. So what will happen, these three resistances will be in series and they'll make up 3R. So we'll get 3R here, and 3R will be in parallel with R. So that will give me something, you can calculate it. Then that will be in series with these two, and that will be in parallel with this, that will be in series with these two. So that's how you do a standard problem. But in this problem, this pattern actually goes on till infinity. Right? This pattern keeps on repeating. So what do you do in this case? It's very simple. If the equivalent resistance between these 2 points, let's say, now I'll use small r for these individual values, all of these are small r, and capital R for the equivalent resistance. Right? So if the equivalent resistance between A and B is capital R, and this system is infinitely long, then doesn't it make sense that if this point is C, sorry, not this point, this point is C, and this point is D, then the equivalent resistance between C and D will also be R. Because if you remove this much, we've got basically the same unit as we had before, but one unit less, the same pattern, 1 unit less. So if it's an infinitely long series, then the potential equivalent resistance between these 2 points has to be the same as the equivalent resistance between these 2 points. So now we have a new problem, A and B. The equivalent resistance between these two is R, and this is R, and this is this is R, and this is capital R now, right? So we've replaced this entire thing with capital R. Now we know that the equivalent resistance of this thing is capital R, so we sort of have R on both sides, the unknown on both sides. So the equation we'll get is R is equal to 2 times small r plus this, which is also in series with these two, and these will give me RR by R plus R. So I'll not solve it now, but after doing that you'll get a quadratic equation, and one result will be negative, so you'll have to discard that, and the other rule will be the answer. So the important point here is, because it's an infinite series, this particular system is exactly identical to this particular system, which is exactly identical to this particular system or to this particular system, except 1 unit extra. And when you have an infinite number of units, 1 unit extra doesn't really make a difference. Finally, I just like to take one standard problem and solve it top to bottom, and this problem is pretty much as complicated as they get in terms of the circuits. It's not very mathematically lengthy, so that the video will be short, but it is as complicated as they get in terms of the number of things you have to do. So I'll just draw the circuit first. Yeah, so this is our circuit. It's a complete circuit. It has batteries and it has resistances, right? The batteries have EMFs of 3, 1, 2 and 1. The resistances are 1, 3, 1, 2 and 2. Let's just label some points as well. A, B, C, D. So what is asked in this particular question is the potential difference between B and D, but it doesn't really matter what is asked. I'll just solve this problem completely and show you the potential difference between any 2 points, the current flowing through any wire, and all of that. So our problem is to solve this circuit completely, right? So the first step is to simplify the figure as much as possible. At this point, there's not a lot of simplification we can do, except one thing I can see. This 3 ohm and this 1 ohm resistance are in series, so I'll just add them up and create a 4 ohm resistance. So these 2 points are connected by resistance of 4 amperes. Now again, I have told you once before, there are 2 methods to solve any problem like this. One of them, you assume potentials and you use KCL to get the equations. The other, you use currents and you use KVL to get the equations. I always prefer to assume potentials because you have the freedom in potentials to take any one point to have the potential 0. Now I could take this point to have a potential 0, but then this point would have a potential of -3. And I don't want minuses because they might increase the chances of making an error. So I see that there's a negative terminal here, negative terminal here. So it makes sense for me to take this to be 0 volts, the potential of 0 volts. Right? If you really once you get this question down completely, you can just try to take this as 0 volts and try to solve it, and I'm sure you'll get the same answer. So if I take this to be 0 volts, this is 3 volts. Right? Let's say this is V1. We don't know what this is. So what is this? This is V1 minus 1, because the difference will be 1. Right? If this is 0, let's take this to be V2. Right? If this is V2, what is this? This is V2 plus 1. If this is V2 plus 1, what is this? This is V2 minus 1. Right? And this is again V1 minus 1. So we see that we actually really needed only 2 variables, V1 and V2, and we were able to write everything in terms of those 2 variables. So I have 2 variables, that means I'll need 2 equations, right? And I have to use KCL. So these 2 junctions seem to me to be quite easy to apply KCL on, so that's what I'll do. So first of all, I'll have to assume, based on what I've assumed to be the voltage, the directions of the currents. So we'll just assume between V1 and V2 one relation to be consistent. I'll just assume V1 is greater than V2. We might not need it somewhere, or we might, but I'll just assume it for the sake of getting directions of currents. So if V1 is greater than V2, right, we'll just, then in that case this has a potential of V2 minus 1, this has a potential of V1 minus 1. So this potential is greater than this, so current is flowing in this direction, right? Here we can assume anything. So, and in this point, because this is a negative terminal, I'll just assume current is flowing in this direction, right? If current is flowing in this direction, then here current has to be flowing in this direction. Once you've decided that, everything else is decided. Current is flowing in this direction, it is flowing in this direction, and it is flowing in this direction, right? So again, I would suggest to you that you assume different directions of current. You assume V2 is greater than V1, then this would be the direction of current, and ultimately the answer will come out to be the same. But you can't assume a direction of current before assuming a relation between V1 and V2. Once you assume a direction of current, you've already assumed this relation, and you have to assume this relation everywhere else as well, right? So now we apply KCLs. Here what we'll get is V2 minus 0 divided by 1, that is this current, right, plus this is 0 and this is V1 minus 1. So 0 minus V1 minus 1. It's possible that current is this direction, that won't matter, then this will come out to be negative, divided by 2, right? So no, wait, this is equal to this plus the current in this direction. Now what is the current in this direction? This is V1 and this is 3, and we've assumed in this direction, so it will be V1 minus 3 by 4, right? So this is our first equation. What is the second equation? We'll apply it here. So in this direction, V1 minus 1 and V2 minus 1. So what we'll get is V1 minus V2, V1 minus 1 by V2 minus 1 actually, so V1 minus V2 by 2, plus in this direction we'll get the same thing, V1 minus 3 by 4 is equal to, and again here we'll get the same thing, that is 0 minus V1 minus 1 by 2. So now we have two equations and two variables, so all we really need to do is solve it. So let's do that now. We'll just multiply the first equation by 4 all throughout. So what we'll get is V1 minus 3 plus 4 V2 is equal to, this is 1 minus V1 times 2. So 2 minus 2 V1, which gives me 3 V1 plus 4 V2 is equal to 5. The second equation will be 2 V1 minus 2 V2 plus V1 minus 3 is equal to 2 minus 2 V1, which gives me 4 V1, no, there's one more, so 5 V1 minus 2 V2 is equal to 5. So these are the two equations. Now the method I always prefer is substitution of one in terms of the other. So what we'll get is, I'll substitute V2 from here into here. So 5 V1 minus 2 times V2. V2 will be 5 minus 3 V1 by 4 is equal to 5. This cancels, gives me 2. I'll just multiply by 2 here, so this will be 10. This will be 10. So what I'll get is 10 V1 and 3 V1. So 13 V1, and this is 5. This will be minus 5, which will go there, so plus 5 is equal to 15, or V1 is equal to 15 by 13. And the potential of this was assumed to be 0, and the potential of this was assumed to be V1 minus 1, so that will be 2 by 13. And as it turns out, 2 by 13 is the answer. The question where I got this from, the question was what is the potential difference between these two, and that's 2 by 13. But if you were asked what is the current through this wire, then all you need to do is, this is V1 minus 1, V2 minus 1. So V1 minus V2 by 2 will be the current. Once you have V1, you can put it into one of these to get V2. So this is, like I said, as complicated as they get, and all you need to do is just assume some voltages and use KCL. You could have done it the alternate way as well. You could have assumed some currents and used KVL. How would that have gone? So instead of all these V, what we would have done is, we would have assumed this is equal to I, this is equal to I1, and this is equal to I minus I1. And then we would have applied KVL through this loop and KVL through this loop. Right, so it would have been going from this direction, we would have added 1, then minus 3, this is 4, sorry. So minus 4 times I minus I1, minus 3, minus 2 times I. Right, so we could assume voltages and apply KCL to get equations, or assume currents, apply KVL to get equations. I prefer the first one because assuming voltages gives you the option of assuming 0 at any one point. Thank you.